Good morning, students. Mr. Carver here. Today we're going to talk about a method that is used to generate functional values based upon a differential equation and an initial condition. And it was a method developed by a Swiss mathematician from the 1700s, Leonard Euler, and this is called Euler's method. Here's the formula for generating the ordered pairs. You've got x sub n, which will be x sub n minus 1 plus h. H is what they call the step. It is the distance between the individual x values. And your y sub n, which is going to be equal to y sub n minus 1 plus h then times the value of the slope of the function at that n minus 1 value. All right, so let's work through a quick example here using this formula. So we'll proceed to the next page, and I'll copy that into the next page. All right, so I've got the formula for Euler's method in the upper left-hand corner. And then the problem is, as stated, use Euler's method to find y of 1 if y prime is equal to y minus 2, and the initial condition, y of 0 is equal to 4. And, of course, the distance between each x value, or the step, is 0.2. So we're going to start off with our initial condition, and then we're going to slowly work our way from 0 all the way over to 1 using these x values. And what we're looking for then is the corresponding y value on the original curve when your x value is 1. And so what we're going to do is we're going to work our way through here using the formula in the upper left-hand corner. And then I'll show you how all of this ties together at the end. So the first then x value is going to be 0.2, and then to get the corresponding y value, y of 0.2, well, that's going to be equal to the y value, the previous y value, or rather is the y value in this case when x is equal to 4. So that's 4. Plus then I've got my step times the value of the slope of the function at the previous point. And in order to find the slope of the function at the previous point, I'm going to use my slope machine here. This is my derivative. And so what I'm going to do is I'm going to take 4, plug in my y value, and I'm going to subtract 2 from it. Put an extra set of parentheses in there for you. And this turns out to be then 4 plus, when I crank all of this out, this gives me 0.4, which means my first y value is going to be 4.4. So this is 0.2 comma 4.4. And then I'm going to continue with this process 4 more times. So let's go ahead and go to the next line. All right, you're free to pause that if you need to. So I'm ready now to get the y value that I'm looking for on the original curve, and I'm going to go through this one more time. Now I've got y of 1 being equal to the previous y value, 6.172, plus my step, which is 0.2, and then again what I'm looking for is the slope at the previous point. And again, I'm going back to use this formula right here. So I get 6.172 minus 2. I follow PEMDAS, simplify that, and that's going to give me 6.97664. Rounded to 3 decimal places is 6.977. That's what I'm looking for here, 6.977. And this is my answer. Now this is what we're finding here. If I were to actually work through this with integration, what I can do is I can start off with this. I can use my initial condition, and I can come up with an equation of the original function that gives me this derivative at this particular solution. So let's just go on to the next page and let's work through that calculus with you. Start off with my differential equation there. I then begin to separate my variables. So I got 1 over y minus 2 dy is equal to 1 dx. I'm going to integrate both sides with respect to y on the left and x on the right. Using u substitution, this gives me the natural log of the absolute value of y minus 2 plus c. That c is going to come to the other side, x plus c. I'm now going to solve using my initial condition. My initial condition is 0, 4. If I plug that initial condition into my differential, or my integrated equation there, that's going to give me the natural log. Let's keep that in blue here. That's the natural log of the absolute value of, what is that, 2 is equal to 0. Writing can be a challenge, is equal to 0 plus c, which means my c is equal to the natural log of 2. I can now take this, plug it back into my integrated equation, leaving me this. Now if I want to solve for y, I'm going to bring e to the other side. This gives me y minus 2 is equal to e to the x plus ln of 2. And of course we know that y minus 2 then is equal to e to the x times e to the natural log of 2. This entire portion right here simplifies to 2. So my original equation is going to be equal to 2 times e to the x, and I'm going to add that 2 to the other side, 2 to the x plus 2. So this is a particular solution to this differential equation. And then if I were to actually plot the ordered pairs given by Euler's method and compare it to the graph of this particular solution, what you are going to see is something like this. And what you'll notice here is the dots right here, I put them into stat plot. Those are the ordered pairs that I generated. It's being f of 0, f of 0.1, excuse me, 0.2, 0.4, 0.6, 0.8, and then 1. And what we're looking for here then is just the y value. The answer that we got was this y value right there. Whoops, don't want to do that. That y value right up there, and that's what the problem is asking us to find. All right, so Euler's method is just a way to generate y values for an original particular solution function without integrating. I hope this helps, and I'll have some extra practice for you guys so that you can practice this on your own at some point. Thanks for watching.